Is it supposed to be warm?
Yeah, during the daytime. It's freezing cold at night.
Are you still sleeping in the basement over there?
Oh yeah.
Isn't it colder over there in the basement?
I have a space heater.
Okay.
Not too sure how the 2 years of spick and span and bleach fumes are treating me though.
Yeah.
Probably doesn't make me better at math.
I don't remember how long I've had these, but I tweaked. Yep. Okay. And no Tom Potter?
No, he would just show up for the test.
I was going to say, I'm not sure I would recognize Tom Potter if I saw him. Okay.
One you don't recognize.
There you go. That's probably a good way to do it. Yes. Him and 7 billion other people, right? There's not really anything in David's notes or in the textbook about binary trees and the kinds of things I'm going to talk about today. So I just surfed around a little bit and found this is a fairly good discussion. And it mostly what I'm interested in today is recursive functions on binary trees, and so he definitely talks about that here. So that's a reading that I've given you. There's a link to it on the syllabus. We're nearly there. I want to talk a little bit about these recursive tree traversals because they're just so cool, and then probably Wednesday we'll start digging into Huffman. Guess.
So with the recursive things on the trees, do you mean like printing type of things?
Yeah, that last thing that I left you with, you know, with the expression, we're going to talk about that essentially the whole time today. The somewhat disappointing aspect, it's not really disappointing. You know, we're going to talk about binary trees and traversals and so forth today. And then I'm not going to let you use a node-based. I'm not going to let you use pointer-based binary tree when you do the Huffman stuff. We're going to use an array-based representation of a binary tree. So all of this stuff is really more theoretical. I don't think that, at least not in Huffman, we won't be using any of this stuff. The reason, and there are sound reasons for why we're not going to do this in Huffman, the reason for an array-based binary tree representation I'll talk about on Wednesday or Friday, whenever I get to it. Okay, so last time we talked about one tree traversal method. I left it sort of as an example, and I want to talk about more formally what these tree traversal algorithms are. They're all recursive algorithms. And let's talk about tree traversals. So I'm going to focus on binary trees, which I introduced last time. And this is a tree with essentially a node structure that looks like this. There's a left child, and a right child, and a parent.
Are you assuming complete binary trees?
No, for now I'm just talking about trees that are comprised of nodes that look like this. They have a left child pointer, a right child pointer, and a parent pointer. So anything that you can build out of nodes like this is a binary tree. Anything. So, for example, a linked list might be sort of a binary. Actually, I take it back. Because a doubly linked list, yeah, I guess that would be a binary tree. You could build a doubly linked list out of this, and it would not be, I don't know. Anyway, here you go. It looks like this. But it might have gaps. Okay. So the tree traversals I'm talking about are all going to be with respect to binary trees. They generalize fairly easily to trinary trees and tertiary trees and so forth. But we're just going to focus on binary trees. So first tree traversal is something called a preorder. And preorder is node, and then left tree, and then right tree. And then there is in order, and that's left tree, node, or root, I guess is a better word, root. And then right. And then there's post order, and that's left, right, and root. And then the last one is not really anything other than a level order is list nodes left to right, from the root down. So for instance, in the level order, if you go up here and do level order, you start here 1, 2, 3, 4, 5. Somewhat artificial. It doesn't really take advantage of the treeness of the data structure. But it is a commonly used tree traversal method. So a really good exam question might be to populate a binary tree with some numbers. Let's do like, I don't know, 33 and 2 and 48 and -1 and 5 and say 17 and 54, and maybe we'll put one more down here, say -8 and 0. All right, and let me build in the nodes here. So a really good exam question is to do something like the in order contents. So remember what in order is. That's left tree, root, right tree, and it's recursive. So you start at the root here and you say, okay, I'm going to print the left tree. So I'm going to go down here. I'm going to print the left tree. So I'll go down here and say I'm going to print the left tree, and then I'll go down here and there is no left tree. So in a sense, I'm done with the left tree. After you print the left tree in order, what do you do? What's the order for in order? Read it to me. So I print the root of the subtree. So I've printed the left subtree at -8. Now I want to print the root of that subtree. So I print out -8. Then I want to print the right subtree at -8. There's nothing there, right? Now I go back up here. I've printed the left subtree. What's the next thing I do? I print the root of that subtree. Now I want to print the right subtree. Okay, now that tree's done. I go back up here. I've printed the left subtree. Now I want to print the 2. And then I want to do the right subtree. Now that's done. I go back up here. I'm done with the left subtree. Now I want to print the root. Now I want to print the right subtree. So to print the right subtree, what do? I go down here, and now what? Print the left subtree, and that's a 17. Now I'm done with the left subtree, so I go back up, and what did I do? 48 there? 48. And then do the right subtree, 54. And now I'm done. So there's an in-order traversal of the tree. Let's do, I don't know, let's do pre-order. So pre-order list, pre-order says do the root, then the left, then the right. So I start up here at the top and do what? 33. Oh, come on. Then I'm going to print the left subtree, right? So I go down here and do what?
Eventually get the
2. Then I'm going to go and do the left subtree, -1. And then I'm going to do the left subtree, okay. So I forgot where I am. I'm at -8. So then I back up and do what? The 0. And then I back up and do what? 5. Back up and do what? 48, good. And then 17. And then 54. And presumably, I'll leave post order to you. But they all give different orderings. And they all have their value. In order and post order are useful for emulating things like expressions, infix and postfix expressions. Pre-order, I don't know, but there's something out there, I'm sure, that likes pre-order. All right. Now, what I want to move on into is let's pretend that we actually have a binary tree class. And it's made up of binary nodes. And I'll, just for the sake of discussion, I'll write out a bnode class. In fact, I'm not going to have a parent in this class. I'm just going to have a left child and a right child. So a B node is going to have a piece of data, and it's going to have a left child and a right child pointer. And then the public section is going to be this is just mostly so that we're all working from this with the same variable names. So the private section, data, left child, right child pointer. The public section has 3 member functions: one to set the data element, one to set and read the left child pointer, and one to set and read the right child pointer. All right, let's pretend, just get this in your head here. Let's pretend that we've got some binary tree. Right, so there's a legitimate way that we could arrange a bunch of B nodes. And whenever you see a missing node, that just means, like, for example, this guy here, the left child pointer is null. So that's how we're going to indicate that there's nothing down there, down below, and left child or right child. We'll just set it to null. Suppose that you've got your binary tree, class. You've been using it, populating it, doing stuff with it, and you're done with it. What do? How? So how do you destroy? You've got to do some kind of traversal.
Post order.
Why post order?
So we maintain the root until
Yes, exactly. We can't do any traversal. We've got to do post because we want to keep that root pointer until we're done with it. So if you go deleting the root pointer right off the bat, then yeah, you've got issues. So I'm not going to write a destructor. I'm going to write a function. What am I going to call this? Let's call it clear, yes. So I'm going to write a clear function, and it's going to take a B node star. And it's recursive. Can you think of how it should go?
Clear left node, clear right node. Oh yeah, that one.
So if root is not equal to null, then do what?
If left child is not equal to null. Oh, I guess it doesn't matter. Clear left child, clear right child.
Is that enough? We haven't deleted anything. Okay, so what do I do after I clear left and clear right? Yep. And there's one more little nicety that I should do before I leave. Yes. Oops. Does this thing have a stopping criteria? Recursive functions should have stopping criteria.
we deleted the original root.
Stopping criteria is you've gotten to a node.
You get to a leaf node.
You get to
or not even a leaf
you
node.
get to a null point.
Yeah. So what happens when I call clear on null? It does nothing, which is essentially a stopping criteria. It doesn't, thankfully, call clear, right? That would not be stopping. That would be continuing. So when you call clear on null, that if statement essentially doesn't happen, and clear just exits without doing anything. So this guy will naturally stop when it gets to leaves. Or really children of leaves, but leaves, right? Because a leaf node, both the left child and the right child are null. So you get to a leaf node, right? And you call clear on the left child, which is null, so nothing happens. You call clear on the right child, No, nothing happens. So now you're at the leaf node. What happens? It gets deleted, gets set to null, and you go back up a level.
And C++ doesn't mind if you call recursively twice in a function?
Nope. Because think about what happens.
Oh, it actually goes all the way through that first bit.
Yeah, exactly.
It's not actually
It goes all the way down. So
That's weird.
it's which node is going to get deleted first in this picture?
The leftmost.
The leftmost node. Yep.
Depending on how you draw it, actually.
In this picture,
Well,
with
you could
the
have-
way.
One's way generations lower, that when you diagram it out, you are more to the left, but it's going to delete the upper left. It's going to delete the leftmost.
Okay, I see what you mean. Yes. Yes. So depending on geometry, I suppose. But leftmost in the sense that the path to get there is left, 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 left. As many lefts as you can get. That's leftmost. It's cool though, isn't it?
So short.
Yeah. It's very cool. So if you were going to write a destructor for, say, a binary tree class, this is pretty much what it would look like. Jamie?
It would still be completely and totally 100% fine if it would clear right before clear left, right?
Yes,
Okay.
absolutely. The other thing is, one of the things that you worry about with recursion is making the runtime stack too deep, running out of resources. And so you might be thinking, well, yeah, this is really pretty, Schuler, but maybe this is not a good use of computational resources. Maybe doing recursive function calls on these binary trees is too expensive. And the beautiful thing about binary trees is they can hold a buttload of data with not too many with not too many levels. And what I mean by that is, right, how many in a full binary tree of, say, let's say a complete binary tree of depth 1, how many nodes are in there? 3, right? Of depth 1, 3. So a complete binary tree of depth 2, 7. So what's the formula?
2 n plus 1 minus 1.
2 to the n plus 1 minus 1? Yeah, I'll give you that. Okay. The way I just framed it, yes. So these things are pretty spacious when you get down in it, right? I can put 1,000,000 things in there, and essentially it's growing like log base 2. Log base 2, log grows really slowly no matter what the base is. So it's not that bad. I don't know what log base 2 of 1,000,000 is, but it's not that deep. Right? Somebody do that really quick? Just do log base 10 of 1,000,000. Oh, well, I know log base 10 of 1,000,000. I'm a dummy. 6. Okay.
19.9.
It's 6. So for log base 2, it's 19.9. That's actually bigger than I would have thought. But anyway.
Base 10 of 2.
Yeah, okay. I'll give you that. So it's 19. So what's the worst? How deep is the runtime stack going to be on 1,000,000?
At worst.
It's not at worst. It's actually at best. It's going to be around 19, which is not that bad. 19 recursive function calls.
Isn't it like? So does it create 2 runtime stacks the first time? Just 1.
It's only just 1.
1 stack gets both clears.
So, right. So the deepest, the most that you're going to get is if the depth is the depth is the depth. That's basically it, right? The most you're going to get is the depth of the tree. Whether it's left, right, left, right, left, right, or what have you, the most you're going to get on the stack is the depth of the tree.
Okay, but isn't it like your answer to Jamie's question earlier? Isn't it like So it sees the left child and then it pauses, right? Because it has to define the rest of the function. So then it goes all the way to the left, but then it has to go back and do the right ones. But do they end up stacking out as they are visually?
So it goes all the way down to the left,
Right.
right? And then it backs up, and where does it go?
To the right.
Right, but it's still got all these guys on the runtime stack down to that guy, and then it adds one more to the
So
right.
it's just like another command on the same stack.
On the same, yes.
Okay.
And then it backs up, and then it backs up, and then, yeah. So the worst you're going to get is the depth of the tree. And like I said, these binary trees can hold a lot of data for not too many levels. So people do use these recursive function calls in practice when they're working with trees. There's really very little risk. Like for example, pretend you had just a one-dimensional linked list and you were doing sort of recursive function calls on that, and you had 100 things in there, right? And you wanted to do a recursive. You would have a runtime stack going up to 100 to get to the end before you started backing out. Whereas you throw 100 things on this guy, and I don't know what you're at, but not much, right? 5 or 6 levels. All right. How about, what's another thing that somebody might want to do to a binary tree? How about, let's talk about copying a binary tree. So you've written a destructor. Now let's say you want to write an assignment operator overload.
Oh boy.
For a binary tree. So you've got a binary tree and you want to copy binary tree B to binary tree A. Again, let's not make it an assignment operator overload. Let's just write a function. So I'm going to feed this function the root of a binary tree comprised of B nodes. And when I'm done, I'm going to get back a pointer to the root node of a copy of that binary tree. A faithful copy, no entanglements or anything like that. All right.
As I'm typing this out, so with the stars, there's like variable type star variable, and then there's variable type star variable, right?
Yes.
Are those two entirely different things?
They're the same.
Okay.
Yes. All right. So let me start out here. B node. In fact, let me emphasize that a little bit. The thing you have to worry about when you're using star is the second star. So if I do B node star, and whether I put it there or I put it here, that's going to make L child a B node pointer. But this star here will have no impact on this guy, so that will actually just be a B node, which is not what you want. It's a really common programming mistake.
Yeah, that makes sense.
So if I want these both to be B node pointers, then I have to add a second star there. Let's see, if root is null, return null. So if I give it an empty tree, I get back an empty tree, which is good.
But wouldn't we have to destroy or construct, I guess, the original? Or no, okay, just copy it, not assign it.
Right. Now, if you wanted to destroy the original in an actual assignment operator overload, what do you do?
Well,
Yeah, call that thing that we just talked about.
Yeah.
I can't remember if I put this constructor in my B node or not. I'll check in a second. All right. Just briefly talk about this, and we'll fix the constructor in a minute if it's not there. If I feed the copy function a null pointer, then I'm not going to do anything. Make sense? So that's the stopping criteria. Otherwise, I'm going to get a pointer to the left subtree, to a copy of the left subtree. And then I'm going to get a pointer to a copy of the right subtree. And then I'm going to make a new node that has the data in the current node, and then the pointer to the left subtree and the pointer to the right subtree. And then I'm done.
I have a question.
Yes?
Does that syntax actually work with the arrows and the commas, or is that just the shorthand for multiple, or not binary on multiple lines?
The return new B node thing?
Yeah.
L-child and R-child aren't part of root. They're part of root.
Yes, L-child and R-child actually are pointers to the left and right subtrees, respectively. So what might be confusing you is the fact that I'm pretty sure I didn't make a B node constructor that looks like that. So up here, I would also have a B node, and it would take a piece of data, so a B item, and it would take a B node star and another B node star. And this will construct a B node with B item data and B node and a left child and a right child pointer. So then when I get down here and I create a new B node, that first argument is going to set the data, and the second two arguments are going to set left and right child. So is that clear to everybody? Yes?
So does this, as we have it set up, does this just copy you a single node? Oh, the copies, never mind, it's fine.
Is everybody good?
Good is a strong.
Yeah, I know. It's a thing of beauty.
It's cheating. It's just,
I know, I agree.
It's just not fair.
Recursive functions are a lot like cheating for some reason. They just don't seem to actually do anything. So as I said before, the way I like to think about it is make a copy of the left subtree, make a copy of the right subtree, and then return a node that joins those two guys. And yeah. How about, somebody was talking about printing. We're not going to print backwards, but how about like a pre-order print? So something like void preprint. And this will take a const B node star.
Okay, this is a function, not a member.
It could be a member, I guess. I mean, yeah, but then you wouldn't have to pass a root to it. Yeah. But all of these things could be made member functions with appropriate tweaks. But yeah, so this preprint thing is going to take a const B node star that's a pointer to a binary tree. And we would like to print out the contents of the binary tree in pre-order. So
pick out the root data.
Need a stopping condition. Right? Okay, so stopping condition, and then you're right. Okay, so then, what was it?
See out root data.
Yep. And?
And pre-parent out child.
Yep.
Since we're not in number, then we need the root arrow.
Yes. Sorry about that. I'm mixing my notes here and what I'm writing on the board here, but yes, root L child and root. Hold on. These are they yeah, references the pointer. That's exactly right. Try not to think too much about that. Yeah, these guys, when you call them, essentially turn into B-node stars for the left child and the right child. So I'm using that trick that I introduced in homework too, where you can read class data and write to class data using the same.
Return by reference.
Yes, exactly.
Okay.
Yeah.
That was really what I was.
Yep, it's returned by reference. What if I want to do post order?
And just move the C out to the bottom.
Exactly. And in order, I can move it into the middle. In fact, the hard thing here is to print level order.
Probably don't do that recursively.
You don't do it recursively, and you don't often do level ordering. Level order is actually pretty easy in an array-based binary tree, but it's actually a pain in the butt in an actual node-based binary tree, a pointer-based binary tree.
Well, if we added a depth parameter to them, that'd be kind of tough to actually like keep track of. I mean, that would pretty much solve the problem.
Yeah, when you get to a certain depth.
Yeah.
The problem is
Traversing it still, though.
Yeah.
Yeah, so it's hard.
Or like store within the node, have each node know what its depth
Well,
is.
you can know what it is, but you don't know how to get to the next one. You might be over on another branch in the same level.
So I can tell you
So you just traverse your tree.
off the top of my head.
Like traverse the show.
Off the top of my head is what I would do is I would allocate a temporary array with enough space to hold the tree. Then I would do the traversal in whatever order I like, and then I would stick the leaf node in the correct position in the array-based listing. And then when I'm done, I only have to do one tree traversal, and then when I'm done, I just list out the contents of the array. Because it's easy to write a formula. I say it's easy, and then I'm not going to be able to do it on the fly, but it's easy to write a formula to figure out where this should go in the array-based, like what level, right? So the first level, or the 0 level, has one element in it, right? So the first element in the array has the root node. The second guy is the leftmost guy in the first level, and then the third, and then the right. And you can actually write a formula to tell you how to tell you where to put those nodes in that array. Yes.
Does that require the add a complete binary tree?
You could probably do it.
Or you can still, like,
No, what you could do is you could just stick something in the array to indicate that there was nothing there.
Okay.
So you would need some kind of flag.
So
Yes.
the array would basically just be like a staircase, I guess, if you will.
Yeah, like each level gets longer and longer and longer.
Would you have it be two-dimensional, or like each?
I would make it a one-dimensional array.
Okay.
And just, here's the root, and then here's the next 2, and then here's the next 4, and then here's the next 8. and so on, and just have it getting longer as it represents
So you don't
more
really
levels.
need to have like flags in between because it's all just based off.
Well, I could put some flags in there, like, let's say this is a tree of positive integers. I could like throw a negative number if there's something empty in there. So I could initialize the whole array initially to be all -1.
Or
And
you
then
could-
I could
or you
just
make the array be pointers and then do a null pointer for the system.
True. Lots of different ways. We'll talk a lot more about array-based representations of binary trees on Wednesday. All right. Yeah, so now that we're thinking this way, I found a pretty cool online demonstration of this. Is this me? Nope, wrong one. So let's go to Yep, that's the one. No, apparently. Oh, I shouldn't type that in the search box, should I?
Lesson 1.
All right, so this little app, it's kind of hard to see, I know, but this little app runs some binary tree exercises. I can click this button and make a different tree if I'd like. And you can have it sort of manually show you sort of how pre-order, in-order, and post-order works. Let's do pre-order. And you can also test your own understanding. Let me find a slightly smaller one here. Let's try that. So I could do like post order here. Oh crap. Abort. Make a tree. There's a good one. And let's do I'll try it and do post order. So post order, remember, is left subtree, right subtree, root. Left subtree, right subtree, root. So left subtree, there is no left subtree, so do the right subtree. There is no left subtree, so do the right subtree. There is a left subtree, so this is the first guy, right? Now go up here and do the right subtree. There is no right subtree, so I'll do root. I'm finished with the right subtree, so do root. Finished with the right subtree, so do root. Here, what do I do? Right subtree here. Left here. Left, done. Right, left, good. Good. Here. 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 Very good, that's correct.
Will it show how it traverses level order, or will it just?
Oh yeah, let's look at it. See, I didn't even notice it had level order. Let's do make tree here, and let's try. I have a feeling it won't. Oh yeah, and well, I mean, I can do. Forget it.
I think it goes from top to bottom.
Oh, it's top to bottom. Yes, exactly right. Let's abort this, yes, and do show me. And I don't think we're going to get any sense as to how it's actually doing the calculation. Yeah.
Oh.
You know, an interesting thing to think about is, would the addition of any extra pointers in the B node help? Or any information in the B node help?
Siblings would.
Sorry?
Siblings would make it a little bit easier.
I actually don't think it would, unless you can convince me.
The depth one, you could do it if you did n traversals where n was the depth, the maximum depth. Because you could go through and do a post-order traversal with, but only print if depth was equal to n, and then do it again only printing if depth was equal to n minus 1. And so it would take more, but I think you would do it.
Right. Yeah, so you would end up crossing some edges quite a lot.
Yeah.
Yeah.
Could you just do, if you had a depth member in each node, you could just traverse the tree and throw them all into a linked list, and then sort them by depth, such that if two have the same depth, they don't get switched. Right?
I was gonna say, I think.
Yeah, you could do that.
It totally matters whether you go top bottom or bottom top, and actually bottom top is really tough because we actually have to identify the location of the deepest and or deepest several nodes.
Mhm.
Versus if you just start at the top here, then the sibling thing we're talking about can work. You go top, then you go left, then you go sibling. If sibling doesn't, and if sibling, and then you go left, sibling. If sibling doesn't exist, oh wait, it always must. Or if it doesn't, then you go down another level.
No, but you don't go
Well,
down.
but
to
then
that
you
level,
can get
gotta
both
jump.
siblings.
Yeah.
You have
Well,
to
no,
get
that's
the
what I'm saying. You
cousins
actually
too.
have to have
cousins as
sibling
well.
link up those in advance. So it would link
Oh.
17 and 63 right there.
Oh, but
So
that's
you
not
have-
what
you
siblings
have
Those would be cousins.
Yeah, I'll find cousins. The worst.
Okay, so
And the cousins.
256 cousins.
so what you're going to find, I think the standard solution is what we'll talk about with the Huffman. It would be to allocate a temporary array and go through just a single traversal and put these guys in the correct location in that array.
I don't know what the correct location is before looking at the tree.
Because
It's like you were saying, Evan, right? If I know, if I put depth markers in all of my nodes, then, and I do like a left, let me think about this, like a left-right traversal, then I know that all of the guys that I encounter at a single level are already going to be in order.
Oh, because you're going top.
No, I know. I just know where to put them. Maybe I don't. Let me think about it.
But you don't know how many there are of any of the other types, right?
I think I have to have a complete binary tree. But if I have a complete binary tree, then I can do what you suggest, right? If I do a left-right traversal, and I don't care where the node is. If I do a left-right traversal, then all the guys at the same depth are going to be already in the right order. So yes, I need a
If it's
complete.
incomplete, you can do that too. But if
It gets
it's
harder to know where to put them in the temporary array.
Right, because you don't know
Right.
how many of each different.
So if it's a complete binary tree, then it's easy. If it's an incomplete binary tree, then I have to think about it.
bubble sort's a stable sort, right?
Yeah.
So we'd be able to use that to sort by depth.
In a link.
But what are you going to be sorting on, right? Those numbers could be all over the map.
You're sorting on depth. That
Because if it's a stable sort, then it should keep everything in order, and then
Yeah.
it should be.
because it doesn't switch methods.
Right.
That's possible. See, now I'm out of time for talking about what I wanted to talk about for the last 5 minutes. Next time, instead of giving you the file or giving you the inputs that I'm going to test your bit streams on, next time we're going to have a discussion about what that should look like. So, because I was thinking about it last time, and I think it's okay for me to have given you my test inputs for the last problem, but part of becoming a good programmer is being able to figure out what you need to test. when you're writing a complicated program. So I thought it'd be worth having that discussion today, but now Wednesday, having that discussion about bitstream. What are some of the things that you're going to do to make sure that your bitstream is working properly? Jamie?
Are there going to be things that will be, like on the last one, there was a list of things that we should pop out if there were errors. And are there, I don't know, I felt like on homework 2, I guess. Or wait, no, the calculator. The calculator one had the...
No, you can just assume that the user is using this thing correctly.
Okay.
Yeah, I'm not worried too much about error checking, because this is going to be utility
Yeah.
in a larger program.
Well, it'd be pretty tough to have an error, because you'd have to...
And the only kinds of things I'm thinking is like trying to set the bit to 2 or something stupid like that.
Or having
Yeah.
like Unicodes in the input file.
Yeah. Anyway, we'll talk more about that on Wednesday.